Hello students. In the previous lecture, we have started looking at uh, how an instruction would be executed at the hardware, right? So we left with a thought that typical execution would involve 5 steps, namely fetch, decode, ALU, then fourth step would be the memory access, fifth step would be the register update. Now if we want to see what happens in each of the steps, in step 1, the using the PC we fetch the instruction from the memory, right, and place that instruction in IR instruction register. In the second step we look at the contents of IR and decode the instruction, and uh, at that moment we will also know what are the source registers that are being used, and we contact the register file and get the values from those registers. In the third step, those the values we get from the registers would be driven to ALU, and ALU would perform the operation specified like add, subtract, etc. Um, for the arithmetic and logic instructions. In case of the load stores, we said in step 3 the effective address would be calculated, and for the control instructions, specifically the branches, we can assume that the ALU would perform the condition check. In the fourth step, the memory access would happen for the load and store instructions. What it means is the effective address that we calculated in step 3 would be sent to the memory, and along with that, if it is a store instruction, we also send the data, right, and the memory would send the data back in case of a load instruction. And in step 5, what we would typically do is we would update the destination register. This would be either the result of the ALU instruction, or it can be the reply that we get from the memory in case of load instructions. And for the JL and JLR kind of instructions, we would like to store the PC in the destination register, right? So let's look at these execution steps from the hardware perspective, how they would happen. A quick note here, a register update sometimes is also called as write back step or write back stage. If you look at the hardware that is involved, this is where I left in the the last lecture. We have the processor memory interface with the memory address register and memory data register. Along with that, we have something called as instruction address generator, which would give us the PC. Along with it, we have the instruction register that has the machine code of the instruction itself, and we have the register file which has all the registers, and we have the ALU itself. In addition, we have the control circuitry which would drive all the required signals among these different logic blocks so that the proper execution of an instruction would take place. Now let's take each type of instruction and see how these uh, modules would work. Uh, Before that, a quick detail into what a register file would typically look like, right? So it is, as you are aware, is a small and fast memory, right? It works as fast as the ALU itself, and we can imagine that it's typically made of edge trigger flip-flops and sometimes very high speed SRAMs themselves. But here I'm taking the example of an edge trigger flip-flop itself. The D flip-flop, uh, on every positive edge the input would be sampled and it would maintain that stage till the next positive edge, right? If we don't want to change the input, then it would be selecting 0 by appropriately setting the RIN, right? If you want to write a new value, that would be uh, given to the other end of this mux, and it would be picked appropriately, right? This happens for every positive edge. Now imagine an array of such D flip-flops. For example, for RV32 that we are currently studying, we have 32 bits in each register, right? So we have 32 such D flip-flops, and in general we have 32 such registers. So imagine a 2D array where you have 32 cross 32 D flip-flops. Now all these elements would need to be accessed, written, or read from. So appropriately we need to give the peripheral circuitry also, which will help us to identify one set of 32 day flip-flops, and each of them would give us one bit, so we need to collect them, and if we want to write, then we need to supply the new value 1 bit each to each of these 32 D flip-flops. Now, if we look at the peripheral circuitry, how would we decide on the number of inputs and outputs to this array? Here, the ISA would help us. How? We would, if you look at the ALU instructions, we will know how many of the register operands are there. So for example, in RISC-V, we have 2 register operands as source and 1 as the destination. So this register file would should be designed to handle 2 register read inputs and 1 register write input, right? And will this hold for other instructions also? If we want to look at how many register operands are there in a load instruction, it is 1 source register and 1 destination register. And when it comes to the store, both the registers are source registers. And for control instructions, for branches, we would read 2 registers, and for the jump instructions, we would read for JLR, we would read 2 register, we read 1 register and 1 write to 1 register. For JL, we simply write to 1 register, right? So as a whole, 2 input ports and 1 output port would be, oh sorry, 2 output ports and 1 input port would be sufficient. So if we imagine the register file to be a black box, let's say it has an input address RS1, address RS2, the second source register, and when these addresses are given, the register file would give us the data out of both the data stored in RS1 and RS2, right? So we would say it has 2 output ports. In the same way, we would need 1 input port, meaning the destination register's address is given to the register file along with the data that needs to be written, and it will handle the write and update the individual flip-flops. So it would be said that this particular register file has one input port, right? And all these need to be synced with the clock, so there will be a clock input. Now if we closely observe, each of these connectors has different width. For example, these ADDR, RS1, RS2 and RD are 5 bits 5 bits. So you can imagine these have 5 lines. Clock can still be assumed to be a single line, and the data RD, data RS1 and RS2 are 32 bits each, right? And again, the ISA would determine these the number of address lines and the data lines, right? Now if we want to understand how a register file would handle 1 input port and 2 output ports, right? And one of the implementation can be, let's assume there are 2 register files, both are completely in sync. It means that the same data will be available in both of them, and let's say one of them will supply us with the data RS1 and the other would consume address rs2 and give the data rs2. Now, we also need to take additional care that if you want to write to a register, we need to do it in both of these copies, right? So the address RD and the data RD would be sent to both of them. So this is one such implementation, and both of them will be driven by the same clock. But what I would pause here and mention is the dotted box is our level of abstraction. We are not going to dive into the register file any further, but we would assume that it can handle 2 output ports and 1 input port. What I have given is a very basic and implementation on how you can it will help you to visualize how it would work, right? Moving on, now let's look at the ALU itself, right? ALU, like I mentioned in the previous lecture, you can imagine it as a collection of all the individual logic blocks, like the adder, right? It can be the ripple carry adder or carry look ahead adder or anything like that, and Brute's multiplier and circuit that will help us for division and shift operations, etc., and even the condition checks, right? All those again, imagine that it's a black box and it will do the operation that it needs to perform. Now we have the register file and the ALU. Let us consider a single instruction add x3 x2 x1, the simple add instruction from Lec2, and see how it gets executed. The register file we have with 2 output ports and 1 input port along with the clock. So the addresses that we give to both rs1, rs2 and rd here would be, so we have our x2 has rs1, so the 5-bit representation would be 00010, and for x1 it would be 00001, and for x3 it would be 00011. When rs1, rs2 address are given, we assume that the register file would give us the values that are stored in x2 and x1. Those will be the inputs to the ALU, and the ALU will perform the addition of these two values, means the values in x2 and x1, and it would be the input C to the register file, which is the data RD. So the RD is x3 00011, and it would be written with a value which will be given by the output of ALU. So this is a simple way we can imagine that register file and ALU are connected in order to execute a simple add instruction, right? Now, if you want to extend it further by considering the subtract and or multiplication, etc., right, even the shift operations, etc., we can imagine that rs1 and rs2 will be given to the register files. They drive the two inputs to the ALU. ALU will perform the specific operation, and that will be fed back to the register file as data in RD. Now, the key point here would be the control circuitry that I pointed out earlier would determine or signal the ALU the operation that it needs to perform. How does it do that? In the decode stage, it looks at the opcode function 3, function 7 values, and it determines which operation needs to be performed, and it would give appropriate signals to the ALU, right? And as an example, if you consider that we are building a hardware to handle 8 different ALU instructions, then the control unit needs to generate 3 signals, and each of those signal, for example, 000, let's say, would indicate an or add operation. 111, let's say, would indicate an AND operation, right? So those signals will be generated by the control circuitry, and the ALU would perform the required operation. Now this would work for the simple add, subtract, etc. Now let's see how this circuit needs to be changed to handle an immediate operation, right? Here we are considering ADD, I, X3, X2 and 100. So again we have the register file and the ALU. Now we are introducing a new mux, namely mux B, right? Excuse me. So this mux B, one of the input would be the value of register B, means RS2 itself, and the other input would be the 12-bit immediate value. Now with this small change in the circuit, let's see how we can execute ADDI. So RS1 would be X2 00010, RD would be X3, means 00011, and we don't have RS2, so we can assume that it's don't care, and the immediate 12-bit value would be 100 in decimal, and because it's a signed value, so the 12-bit would be sign extended appropriately. Right now with these inputs, we expect the ALU to be taking the value 100 and the value in X2 driven by A. It would perform the addition and write it back as an input C, which will be returned to the destination register X3. Right, again the control circuitry needs to generate the select signal for this mux B. As a quick example, if it were an add instruction, then the control signal would be so that mux B would select B. If it is an add I, then it would select the immediate value. Now let's try to imagine this hardware working in stages or steps. Right, here we have the connections that we have discussed thus far, and here are the steps. So in step 2, we are going to identify the source registers and destination register and read the values from the source registers, and by the end of step 2 we can assume that the value A and B are ready, and also the immediate value is extracted and sign extended. At the beginning of step 3, the ALU will pick the values at its input and perform the operation, and as step 5, it's going to write it back to the register file, to the destination register C. Right now, in the previous class, I also mentioned that for regularity, we introduced the dummy stage as step 4. So what it would mean is by end of step 3, we have the value of the operation that we need to that we plan to perform. But in step 4, what happens is that value will be directly forwarded to, let's say, another buffer ry. Right, in step 5, ry will be the input, will be the driver to the input C. Now that would be for the typical ALU instructions. Now let's try to visualize how a load instruction would work on the same hardware. So here we have considered load double X2, 16, X3. So here X3 is the source register, X2 is the destination register, and 16 is the offset or the immediate value. So we have the register file ALU and mux B, right? And these are the connections that we have seen so far. And to accommodate step 4 for ALU instructions, we have introduced another buffer ry, and that would be the input to the register file in step 5. So when the control circuitry has identified that it's a load instruction and decoded the register operands and the immediate value, these would be the inputs. So RS1 would be 00011, which is X3. RD would be 00010, which is X2, and the immediate value of 16. Now the ALU would take the value in x3 as input A and 16 as the other input to it, add them, and we are saying that this added value is called as an effective address. Now in step 4, the load instruction would, uh, let's say we have introduced another temporary buffer RZ at the end of step 3, right? So why we introduce that? Because this RZ, the value in RZ, which is the effective address, now needs to be sent to the memory, means it will be placed in the memory address register, and the memory would respond us with data by placing it in a memory data register, and that would be written to RY. So accordingly, we have a new mux labeled as mux5. Now, why do we need a mux here? So for non-load instructions, the value in RZ would be forwarded to RY, right? For load instructions, it would be given from the MDR. So accordingly, we need to place the control select signal, and which will be given by the control circuitry. So here the control circuitry would signal that the immediate value needs to be picked as an input to the ALU, and in step 4 it will generate the signal so that the value in MDR is written to RY, and in step 5 RY would be the input terminal C for the register file. So in this way we can execute the load instruction. Now let's consider the store instruction. Here we have the store double x2, 16, x3. Both x2 and x3 are source registers and 16 is the immediate value. Now here are the overall connections that we have seen so far and divided into various steps. Right? For this particular store instruction, the RS1 would be x3, so 00011. RS2 is x2, so we have 00010. There is no destination register, so we can say it's don't care, but we do have an immediate field which is 16. Here 1 followed by 4 zeros in binary. So one small modification that we need to do is excuse me. So the value in from the source register 2, which is B, was earlier discarded here, but this is what needs to be sent to the memory, because that's what the store instruction does. The value in x2 needs to be stored in location which is given by the value in x3 plus 16, right? Now accordingly, the value B is forwarded in step 3 to a temporary buffer which is RM, right? So in step 3, along with this forwarding, the actual effective address calculation will happen, and by the end of step 3 we have the effective address in RZ. So RZ in step 4 will be forwarded to the memory address register MAR, and the value in RM will be forwarded to MDR. So the memory is expected to consume this address and data, right? And let's assume that it gives us an acknowledgement saying that the store is done, and by the end of step 5, sorry, by the end of step 4, uh, the operation is done, and there is nothing specific that we do for store instructions in step 5, right? Now I have included another input here, which is return address. This is specifically needed for the control instructions. So I'm going to explain the control instructions in the next class, but as such, you can see that the present connections will be um, present connections among these hardware would help us execute any of the ALU instructions, even their immediate versions also, and the load and store instructions. So I'll pause this lecture at this moment. Sorry, I think I missed this. So the control circuitry of the MUX5, which I have already spoken earlier, will come in handy for the control instructions also. So I'm going to talk about it little more or very much in detail uh, in the next class, which is dedicated for the execution of control instructions. With that, I will pause this lecture. Thank you, and sorry for the disturbance at the fag end of the lecture. Thank you.